As promised, we're going to work through an example of oscillations. We're going to look at masses on a spring. So let's start with a spring, and we're going to put a mass on it. And the spring's going to have a spring constant of K, the stuff we've covered before, and it's going to have a mass of M. And we're going to push it back and forth. It's going to oscillate back and forth like this. And everybody's happy, and this thing just moves back and forth in a little bit of a mesmerizing, sort of hypnotic sort of way. But let's think what happens if we were to draw the free body diagram when it's at any one of its positions. And I'm going to draw it at its maximum position. So when it gets to the maximum position, I will pause it. This little diagram is going to keep going. Just ignore it. But we're going to look at the free body diagram for this block. So we know that this thing has a weight force pointing down. We're assuming it's resting on a table, so it's going to be frictionless table, so it's got a force up. Don't really care about those. What we do care about is the force that when it's at its maximum displacement up here, the spring is going to be pulling it back. So there's a force due to the spring. And that force, based off of Hooke's law, is minus kx. So x is the distance from its average position, its center point. We pull it over. Minus k is going to be given by the opposite of the spring constant. So, like normal Newton's second law problems, we're going to write stuff down. And I'm going to choose in my diagram that positive is going to be towards the right. So I write down that the sum of the forces is equal to mass times acceleration. Net forces give us our acceleration, and we're only dealing with the x direction because the y direction is just going to cancel. So I write down that my net force, I only have one force in the x direction. It points in the minus kx direction, and I set that equal to ma. And the ma is just from Newton's second law again. So now I look at this equation, I rearrange it, and I notice that I have a is equal to minus something times x. This is exactly the equation that I had before, except for I have this k over m instead of that omega squared. So my equation, this acceleration related to the opposite of the position, this is going to give me harmonic motion. So I'm just going to define omega squared to be k over m. And that's what's going to happen is when we substitute back in, we come up with that familiar equation. So this equation satisfies that harmonic motion, this oscillatory motion, so we can instantly write down the position. Position has a new maximum amplitude of x naught. I used to call it a, I'm calling it x naught now. It's going to be a cosine function because I'm starting off with the maximum amplitude out here. And instead of having omega in here for this term, I substituted in, using this substitution, I substitute in the square root of k over m for omega. So I can see that x equals x naught cosine of the square root of k over m times t, and again minus this phi, which is our phase shift. So could write down the velocity terms if we really wanted to, or the acceleration terms. They're going to be related. They're going to be exactly the same thing through, except for we just showed that this is the only substitution we have to make. So the oscillation of the spring, and if we think about back to what omega is the angular frequency. It's related to the period. The period of oscillation of a spring is given in terms of this relationship of k over m or m over k. One of these values will be able to describe the frequency or the period of the oscillation. So in a spring mass system, the mass of the object determines how long its period is, and the stiffness of the spring will determine how long it takes for this function to repeat itself. So this will give us some powerful tools in solving stuff later on.